David will talk about his recent work on order-revealing encryption.
Cool. Thanks, Amit, for the introduction. So I'm David. I'll be talking to you about order-revealing encryption, or how to search on encrypted data. This is joint work with Kevin Louis. So in the last couple of years, a trend that we have been seeing is that databases get compromised. Just a couple months back, we saw that Yahoo says databases got compromised, and names, email addresses, and many more information were publicly exposed on the internet. This is not a problem that's only limited to Yahoo. In fact, Anthem experienced this a couple years back, or I guess 1 year back. The US voter registration database, somewhat infamously Ashley Madison, eBay, LinkedIn, and so on. All of these have experienced database breaches in the last couple of years. So what this sort of shows us is that data breaches have become increasingly the norm rather than the exception. And increasingly often, databases get compromised and customer information ends up being exposed on the internet. So the question then is, why do we keep our databases in the clear? Why don't we encrypt the databases so that when a database does get compromised, not all of the information is immediately leaked? And I think somewhat as Yahoo Senior Vice President Jeff Bonforte, when interviewed about this, why Yahoo didn't take precautions about securing their databases, the reason he gave for not encrypting was because it would have hurt Yahoo's ability to index and search messages and provide new user services. And this sort of revisits a tension in cryptography that often comes up, which is we need to have a need to secure our information, but we also have a need to compute over it. And if companies just immediately encrypted their databases, they oftentimes sacrifice a lot of the functionality. Now they cannot use the data or leverage it to provide services and so on. So in order to sort of bridge this gap, and useful primitive seems to be this notion of an order-revealing encryption scheme, which allows us to get a trade-off between some security for encrypted database scenarios, as well as support some functionality over encrypted data. So let me just explain what an order-revealing encryption scheme is. This was a notion introduced by Bonnet, Louis, Rakova, Sahai, Zandri, and Zimmerman in Eurocrypto 2015. An order-revealing encryption scheme, or ORE scheme, is a secret key encryption scheme where a client who possesses a secret key is able to basically encrypt numbers or strings and other values and offload them to a server. And then what the server can do, given only the ciphertext, is basically perform comparisons. The server is able to answer queries such as which value is greater, the one encrypted by the first ciphertext or the value encrypted by the second ciphertext. As you might expect, an order-revealing encryption scheme allows us to perform range queries on encrypted data. You simply given the ciphertext, you can do comparisons, and comparisons enable you to do range queries. So just to make sure that the functionality or the schema is clear, in an order-revealing encryption scheme is an encryption scheme where given any two ciphertexts, there is a public function that allows one to perform the comparison. For those of you that are familiar with a related notion of order-preserving encryption, that can also be viewed as a special case of order-revealing encryption with the additional structural constraint on the ciphertext space. In an order-preserving encryption scheme, the ciphertexts themselves must be well-ordered, and the comparison operation is direct comparison in the ciphertext space. So this was a notion that predated order-revealing encryption and was introduced by Bodreva et al. In 2009. So let me first show you sort of where we are when it comes to order-revealing encryption schemes. And the way that I like to look at the different kinds of candidate schemes that we have today is on a curve where we look at space efficiency on one axis, or efficiency and performance on one axis, and security on the other axis. So the first kind of order-revealing encryption scheme is this notion of order-preserving encryption, which I alluded to earlier. This was the Bodreva et al. Construction. This scheme is very efficient. It only requires PRFs, so only based on one-way functions. But it does not offer much security. And in fact, subsequent work has shown that given even a single order-preserving encryption ciphertext, it reveals half of the bits of the message. And this is under very conservative distributions. So for real-world distributions, the leakage can be much more severe. But it has the advantage that it is very efficient. On the other end of the spectrum, we have constructions of order-revealing encryption that sort of satisfies the ideal notion of leakage. So recall that when I define order-revealing encryption scheme, it's an encryption scheme that allows you to do comparisons. So an ideal order-revealing encryption scheme is one that only reveals the ordering between messages and nothing more than the ordering. So to construct this, it turns out that the current candidates require us to use very powerful primitives, such as multilinear maps or indistinguishability obfuscation. So unfortunately, in exchange for very good security, we get something that's probably not going to be used by companies tomorrow. So earlier this year, we introduced the notion of a practical order-revealing encryption scheme, which sort of is a new point on this trade-off between efficiency and security. And in this work, we're going to further push along this trade-off, and I'll say exactly what the increased security that we achieve is. But just to sort of highlight, this has been a very exciting area, and concurrent with our work, Cash et al., as well as Joao and Pasogyu, they also gave new order-revealing encryption schemes that give us further trade-offs between the security achieved and the performance. So one other thing that I would like to highlight is that in the subsequent schemes, starting from our work earlier this year, we introduced order-revealing encryption schemes where we can actually precisely quantify this leakage. So in particular, these order-revealing encryption schemes are what I call order-revealing encryption with leakage. So in addition to revealing the comparison, they also reveal some additional information. And in these schemes that I highlighted from here on, we have a precise description of what that leakage is. This is not the case for order-preserving encryption, which we know is leaky, but we can't really bound exactly what is leaked. In our current constructions, we have precise leakage profiles. I'll talk about that later in the talk. OK, but the thing that I actually want to address before we get onto the construction is this notion of an inference attack. And so the canonical application of order-revealing encryption that I presented at the beginning was using order-revealing encryption to perform database queries, right? We have a database, we want to encrypt the contents, but we still want to be able to perform search queries over that database. So the natural solution to performing range queries or queries over an encrypted database is I simply take the data, encrypt it using the order-revealing encryption scheme, and then perform the queries using the comparison operation provided by the ORE scheme. So what Naveed and Kamara and Wright showed from CCS of 2015 and has subsequently been extended by Dirac et al. And Grubbs et al. This year, they show that if you take a database that's encrypted under one of these order-revealing or deterministic encryption schemes, some of these encryption schemes that really enable simple computation over the encrypted data, and you combine it with publicly available data sets information, statistical information, and so on, and you perform frequency statistical correlation analysis, what you're actually able to do is mount plaintext recovery attacks. And in fact, for real-world data sets that they experimented on, these attacks are particularly devastating. In many cases, given a database encrypted using an order-revealing encryption scheme, you can actually perform inference attacks and recover 95 to 99% of the data. So basically, this says that if I take my database, I encrypt it under an order-revealing encryption scheme, so I can get some security out of it. It actually provides no guarantees in practical scenarios. So the question then is, OK, this is really bad for order-revealing encryption. Is order-revealing encryption dead? Should we move on to better cryptographic primitives for solving a problem of encrypted search? And to sort of make progress towards answering that question, I'm going to take a deeper dive into the security model and distinguish between two different kinds of security that we're concerned about when we look at encrypted database solutions. So one kind of security is this online security model. This is the case where the adversary is an active one, and the adversary in this case has compromised the encrypted database. And not only that, it's sort of persistent on the database itself. The adversary gets to see the database contents, it sees the queries, and it can maybe even interact with the database. This captures an online active corruption of the database. It tends to be less common, but can potentially happen. And then this is to be contrasted with the offline setting, when we have an adversary that basically breaks into a server and exfiltrates the contents. Basically gets a passive snapshot of the contents of the database, maybe even the contents of the memory on the server at the time. This seems to be the more common scenario that we experience today. And we look in news articles about these database breaches that have happened in the last couple of years. And almost nearly all of the cases is basically the adversary breaks into the server for a short period of time and exfiltrates the data. Now, it doesn't really help us to define these two notions when we consider the possibility of an inference attack, because an inference attack really just requires offline access to the database. The adversary breaks in, steals the encrypted database, and then using public information and comparison and the ability to compare entries inside the database is actually able to recover most of the contents of the database. So the question that we want to answer in this work is really the question of whether we can fully defend against these offline inference attacks while using something that is legacy-friendly, using something lightweight like order-revealing encryption that doesn't require completely redoing the database from scratch. So as I formulated the question right here, it's actually not very well defined. And in fact, there's a trivial solution if all we cared about was protecting against offline inference attacks. The trivial solution is that we just encrypt the entire database and have the client provide the decryption key at the query time. So at the query time, this server will decrypt the contents of the database, answer the query, and so on. So if this was the solution, I wouldn't be standing here today. The reason is that this solution provides absolutely no online security. If the adversary breaks into the server, exfiltrates the database, and even sees a single query, all security is lost. So this is not an ideal solution. So what we really want is a way to use order-revealing encryption scheme to build a range query system that enables perfect offline security. So we want to protect against offline inference attacks. But we also want limited leakage even in the online setting. So even if the adversary gets to see a few queries and breaks into the server for a small period of time, we still want some security guarantees. We don't want the case that the adversary basically recovers everything after observing even one query. OK, so the focus of this talk is going to be on how do we use order-revealing encryption to perform range queries on encrypted data in a way that is robust against offline inference attacks, but still provides some security guarantees even in the online setting. So the key primitive that we're going to introduce here is an order-revealing encryption scheme where the ciphertexts have a decomposable structure. This will be very familiar to you if you have worked with multi-input functional encryption. This is something that's very inspired by that line of work. And so more concretely, an order-revealing encryption scheme with a decomposable structure works as follows. If I want to encrypt the number 101, I take the ciphertext, and the ciphertext, it turns out, can be broken up into two different pieces. And here, for simplicity, I will refer to this as the left ciphertext and the right ciphertext. So the ciphertext have two components, a left one and a right one. OK, and the next observation, or the next requirement that we impose, is that given the left component of one ciphertext and the right component of the other ciphertext, comparisons are already possible. So traditionally, in an order-revealing encryption scheme, in order to compare, I need to give you both of the ciphertexts. In this left-right notion of an order-revealing encryption scheme, I don't need to give you both the full ciphertext. It suffices to give you the left component of one ciphertext and the right component of the other. And this already allows for comparisons to be performed. OK, so this is the additional structure constraint that we're going to impose. And moreover, we're going to now define additional security properties that we want this scheme to achieve. And the key here that underlies our construction is that the right ciphertexts themselves should provide semantic security. So if you only have a collection of right ciphertexts and not any of the left ciphertexts, no information should be revealed. And this precisely allows us to achieve robustness against offline inference attacks. So let me just make sure that's clear by showing you how we can build a range query system resistant against offline inference attacks if we have an order-revealing encryption scheme that has this particular property. OK, so here's my encrypted database. And suppose we want to support range queries over this database. So suppose for each column in the database, what we're going to do first is we're going to build an encrypted index. So we want to support range queries over the age column. What we're going to do is we're going to build an encrypted index, which consists of the following. First, we're going to take all of the entries, sort them, and then encrypt them using the order-revealing encryption scheme. Now, when we encrypt them, we're not going to store all of the complete ciphertext, which consists of both the left and right components. We're actually only going to store the right ciphertext, so only half of the ciphertext, essentially. And then we're going to encrypt the record indices in this table. And the record indices can be encrypted under any semantically secure encryption scheme. So we proceed in this way for each of the columns in the database over which we want to support range queries. And we're going to encrypt the columns here using independent order-revealing encryption keys. So you don't get correlation analysis between multiple columns. OK, so the contents of the encrypted database consists of the following. Consists of all the encrypted search indices. And then we can just encrypt each of the rows of the database as well. So to perform queries and to search and to fetch entries in a database, the client will hold the decryption keys needed. So namely, the order-revealing encryption key, as well as the keys needed to decrypt the entries here, as well as the encrypted indices there. So let's see how we can use this encrypted index to perform a range query in sublinear time. So suppose we want to now process a query for all the records where the age is between 40 and 45. What the client would do is the client would take the order-revealing encryption scheme and encrypt the endpoints of the query. And here, the client will not need to provide, again, the full ORE ciphertext. It suffices that the client provides only the left ciphertext. So given the left ciphertext and the right ciphertext on the server, we already can perform comparisons. So the server will now basically take the index for the age column, take the two endpoints, encrypted endpoints, and use binary search to basically identify which records satisfy the query. And finally, the server returns the encrypted indices that match the query. So server sends back encryption of 2 and 3. The client is able to decrypt because the client holds the decryption keys. And now everything else is pretty standard. Now a client just retrieves the associated records from the database. So if we look at the online leakage, so what does the server learn in this case? Well, it certainly learns the access pattern, but this is almost implicit in most solutions that support encrypted search in sublinear time. So the set of records that the client retrieves is revealed to the server. But in addition, it also reveals whatever the order revealing encryption scheme happens to reveal. So in ideal ORE, this would just be the ordering between the left and right ciphertexts. In our setting, it might be a little bit more information than that. I'll get to the precise leakage profile later in the talk. But this is what happens in the online setting. But what happens in the offline setting? So now consider just the adversary that is able to break into the database and exfiltrate the contents. Well, what that adversary is able to see is basically the contents of the encrypted database, as well as these encrypted indices. And the key observation here is that everything that I've put on the screen is actually encrypted under a semantically secure encryption scheme. So this, in particular, necessarily provides perfect offline security because we have semantically secure encryption of all of the contents of the static state of the database. OK? So let me just come back to this picture of where we stand with respect to order revealing encryption schemes. Do we have order revealing encryption schemes that have this kind of decomposability where one side provides semantic security? So it turns out that the existing constructions do not. So order preserving encryption, as well as our earlier construction from this year, these are basically completely broken by offline inference attacks. And it's very unclear whether they can be adapted to provide this sort of left-right semantic security notion. So I think that these constructions are probably dangerous to use in practical scenarios if you're worried about inference attacks. However, we will also show in this work that sort of the subsequent constructions, including the one that I am about to describe, they can actually be easily adapted to provide perfect offline security. In particular, they have a decomposable structure where one side provides semantic security. And that will be the subject of the rest of the talk. So how do we actually build an order revealing encryption scheme from basically one-way functions that has this particular property? So the high-level blueprint of our construction consists of basically two key steps. The first step that we're going to do is we're going to build a small domain ORE. So what I mean by small domain is assume that you're only going to encrypt small messages. So small messages might be like numbers between 0 and 255, so 8-bit messages. This is not very useful because in practice we're going to be encrypting more than just bytes. So there's also going to apply a domain extension technique, which is inspired by some of our previous work. And this combination will allow us to build an ORE for a large domain, so for an exponentially large size message space. But there will be some additional leakage beyond just the ideal leakage. OK, so let me first show you how we build a small domain order revealing encryption scheme with the best possible notion of semantic security, or with ideal security. This is actually fairly straightforward. So suppose the plaintext space is small, just the numbers between 1 and n. The secret key of our encryption scheme is basically going to be a key associated with each entry in the plaintext space. So we're going to enumerate the elements of our plaintext space, 1 through n. For each one, we're going to associate it with a PRF key. So the secret key is basically k1 up to kn. And if we want to be more efficient, these can all be derived from some PRF. So we don't have to have a very large key in the actual underlying ORE scheme. But for simplicity, let's just assume that the secret key consists of this tuple of keys. So now the question is, how do we encrypt a value I? Well, we're going to actually do it in a very brute force way. What we're going to do is we're going to consider the vector of n elements, where the first I positions have value 1, and the rest of the elements, n minus I elements, have the value 0. So the invariant is all positions less than or equal to I have the value 1. All positions greater than I have the value 0. Now this is pretty simple. Now we're just simply going to encrypt each entry in the vector. So encrypt each slot with the key for that particular slot. To allow a comparison, we can just give out a key for that particular slot. OK? So there is something wrong with this construction, but let's just, for sake of argument, let's just continue. So now, given two ciphertexts, how do we do the comparison? So here we have an encryption of the value I. So we have the key for the I slot. And here we have the key for the J slot. How do I do the comparison? Well, if I take the Ith key and I decrypt the Ith position, I learn the comparison between I and J. And similarly, we can do it in the other way as well. We can take the key for the J's position, decrypt the J slot, and because this is sort of an encoding of all of the comparison responses against every possible value in the plaintext space, this decryption yields precisely that comparison output. But now you might complain that this entirely reveals the index I, and the index I is actually the message that we want to hide in the first place. So this by itself doesn't quite work. But the intuition is there, and a simple tweak will allow us to build a small domain ORE that gets best possible security. All we need to do is apply a random permutation. So instead of encrypting the values 1 through n in the original order, we just permute them. And then when we give out the key, we also include the index of the permuted index that you should look at to decrypt. The second thing to observe is that if you look at this encrypted vector here, this is actually semantically secure. It basically consists of a bunch of semantic secure encryptions. So this achieves best possible security. It's very straightforward to show this. But the drawback is that ciphertexts are very large. If I have n elements in my ciphertext, in my plaintext space, the ciphertext space grows linearly in the size of the plaintext space, which can be exponential in the bit length of the plaintext space. So this is not very useful in practice, but it gives us very strong security guarantees. So the second step in our construction is we're going to extend this small domain ORE for small messages into an ORE for large messages. And the key idea here is we're going to first take our message and decompose it into much smaller blocks, and then apply the small domain ORE to each block, almost. So what are we going to do? Let's take our message space, and let's say these are the bits of the message. So here we're going to look at an 8-bit message space. And the first thing that we're going to do is we're going to split it into smaller blocks. So here I'm going to look at blocks of size 4, but this is a sort of an additional parameter of the scheme. You can set the block size as needed. And we're going to now encrypt each chunk using an order revealing encryption instance where the secret key is derived from the prefix of that chunk. So here, I'm going to take the first block, this 4-bit block, and encrypt it using this small domain ORE. So this brute force order revealing encryption scheme for this particular block. And similarly, I will do it for the second block. But here, the secret key for the order revealing encryption scheme is going to be derived from the prefix here. So just to make that clear, for the first block, we're going to derive the ORE key from the empty prefix. The second block, we're going to derive the key from the prefix here. And this becomes important when we actually go to do the comparison operation. So how do we do comparisons? So let's take our message, and suppose it has 2 blocks. And now we have 2 messages. And so comparison will now proceed block by block. So first, we're going to compare the first block of this guy with the first block of this guy. And the reason we can do that is because they share a common prefix, namely the empty prefix. So the comparison operation will succeed by correctness of the underlying ORE scheme. So and if they say that those 2 blocks are equal, then we can go on and compare the next block in sequence, because that means that they must share a common prefix, and therefore these 2 ciphertexts can be compared. Suppose otherwise, suppose that at one of the blocks, the comparison output is not 0. That means they're not equal. Well, that means that we learned exactly the ordering between the 2 ciphertexts. Right? The ordering is basically the ordering between these 2 blocks. So if we do this block by block, well, in addition to learning the ordering between the 2 blocks, we also learn the first block in the message on which they differ. OK, is this clear? All right. So the next thing I need to tell you is whether this new construction, or the ciphertext in this new construction, whether they satisfy this notion of left and rightness. And this is actually not very difficult to do. So we're going to take the left ciphertext here to just be the left ciphertext of each of these underlying blocks. Similarly, for the right ciphertext. And the key observation, again, is that the right ciphertext by themselves provide semantic security because it basically inherits semantic security of the underlying ORE scheme. So some optimizations are actually possible if we apply this domain extension technique in a black box way. I'll refer you to the paper for the precise details there. OK, so just coming back again to a very familiar graph at this point, just to compare our work with our previous work, in our original construction of practical order revealing encryption schemes, the amount of leakage, in addition to the comparison, was basically the first bit between 2 messages that differs. In this work, we have extended that leakage, or reduced that leakage, so that we can only the position of the first block that differs is revealed. And the block size is now a parameter that can be set depending on the desired security versus performance trade-off. So for instance, we can encrypt byte-sized messages, we can encrypt 2 bytes at a time, and so on. OK, so to conclude the talk, I'm going to give you some benchmarks to sort of show whether this construction is actually practical for existing deployment scenarios. So we actually implemented our scheme. So we did perform some micro benchmarks and compared it to the performance of order-preserving encryption. So this is the sort of the state of the art today. This is the kind of constructions that are being used in practical scenarios. And then we also implemented our original construction as well as our new construction for different block sizes. And we measured the encryption time, the comparison time, and the size of each ciphertext. And this is for encrypting a single 32-bit value. And the key takeaway here is that if we look at the middle column here, if we want to encrypt bite-sized blocks, so basically if you have 2 messages, this will reveal the first byte that differs, so one of 4 possible locations when we work with 4-byte messages. This encryption time is actually extremely fast, and this is because all we require is PRF evaluations. So i.e., we only need AES for everything. With OPE, we actually need to do hypergeometric sampling, which is a more expensive procedure. So we're over 65 times faster than conventional order-preserving encryption schemes. The unfortunate part is that our ciphertexts are now much longer. So that we have a 30x blowup compared to existing OPE schemes. However, we do achieve much stronger security guarantees. And especially if you use the left-right decomposition for encrypted database scenarios, we can actually give a construction that gives best possible offline security, something that is not present in the existing constructions. OK, so to conclude, at the beginning of the talk, I sort of showed that inference attacks render most conventional encryption schemes or database encryption schemes based on property-preserving encryption, so order-preserving, order-revealing, or deterministic encryption. These kinds of encrypted database scenarios are basically completely insecure, given the current state of attacks. However, hopefully I've demonstrated in this talk that order-revealing encryption can still be a useful building block for designing encrypted database scenarios, but we have to apply them in a less direct way. If we just directly apply them, then the inference attacks will completely destroy them. But in this other fashion, if we consider this left-right notion, then we can actually use ORE to build an encrypted database system that is mostly legacy compatible and provides very strong security guarantees in the case of offline attacks, as well as some security in the case of online attacks. And I've also given a new construction that sort of achieves the security notions put forth in this left-right framework. And in the paper, we also give new impossibility results on what sort of security is achievable using order-preserving encryption. I did not have time to describe them in this talk, but feel free to ask me about them afterwards if you're interested. So let me just conclude with a few open problems in this area. So one of the open problems on the practical side is really looking at what kind of inference attacks are still possible. So they're particularly devastating to all the schemes previous to this work. What sorts of inference attacks are still possible in our setting? So certainly in an offline setting, if we use our new range query system, there are no offline attacks. But in the online setting, what can we learn? And here's some intuition for why the leakage should not be as bad as it was in the offline setting. So one scenario, or one difference between our current construction and previous constructions, is now that we encrypt these columns independently under different ORE schemes. So multi-column correlations are much more harder to infer. So this was a source of some of the more severe attacks on ORE. It's much harder to mount those kinds of attacks in our current setting, but I'm not saying that they're impossible. And secondly, we have a more limited leakage profile. There's only leakage between left and right ciphertext. There's not much leakage between the right ciphertext. So hopefully that offers additional security guarantees as well. But again, we would have to do some kind of empirical study to really determine the ramifications of our new leakage profile. So on a more theoretical side, on constructing order-revealing encryption schemes, I think there are also some very interesting questions that can be explored. So one question, so this is slightly less ambitious than trying to construct ORE from simple assumptions, is can we even just build a small domain ORE with best possible security where the ciphertexts are sublinear in a plain text space? We don't know how to do that. The best solution we have is sort of this linear brute force solution. Can we do something square root? Can we do logarithmic? That's completely open. And lastly, can we construct left-right OREs from PRFs where both left and right ciphertext provide semantic security? So we know how to do this now from pairings, but we don't know how to do it from one-way functions, which I think would also be interesting to explore, because that would further reduce the leakage in practical scenarios. So with that, I'll open the floor to questions. Thank you very much. Right. Yes, so that's a good point. So basically, when we do at the time of index construction, we would pre-sort the index. So the index would always be maintained in sorted order on the database side.
So that's going to involve a lot of interaction with the client then, right?
No, so at the beginning of time, when we set up the index, we would construct the index in a sorted order. And then later on, when you want to do dynamic updates, you would provide both the left and right ciphertext for your update. And then you can figure out where to insert in the database. So to perform the range query itself, we only need to provide left. If we want to do the insertion or deletion queries, we will provide left and right.
I see.
Mm-hmm.
And the service throws.
Yes, so we have to trust the server to forget previous queries. Mm-hmm.
Any other questions?
Yeah.
Would it be possible to just quickly go over the domain extension again? I'm not sure that I.
Oh, OK. So yeah, let me see. OK, so the main idea is the following. So we take our large domain, right? This is an 8-bit domain. We're going to split it into blocks based on the size of the small block size. And basically, we're going to apply the small domain ORE to each of the blocks in order. And basically, the key used to encrypt this, so the ORE key for the small domain, is going to be derived from the prefix. So the prefix is basically all the blocks that precede it. OK? So what this would entail in this case is I take this first 4-bit block, encrypt it using an ORE key derived from an empty prefix, and that will be the first ciphertext block. And then we repeat for the second guy. So for this block, we also encrypt it using a small domain ORE, but the key for this small domain ORE is going to be derived from this prefix block.
How do you use it in some hash function or something? How do you derive it?
We can just derive it using a PRF, so part of the secret key in the ORE scheme. Yes. Does that answer your question?
Yeah,
OK. OK.